So today's agenda was a bit ambitious. Now that I go back and have a look at what I actually put down as the topics to cover, um, I highly doubt we'll get through all of it, even though some of it is more so revision stuff. We're going to have a look at the circular functions stuff, and some of it will be some of the refresher on trigonometry. But for the most part, we're going to be looking at the actual either the solving or the evaluating of circular functions and how we use the unit circle to achieve that. And additionally, then I also decided to, at least on the agenda, put on some other nuances as well as like some further insights into the unit circle. We're probably not going to get there though, so we'll just sort of go as far as we can, and I'll update the curriculum to fix things up afterwards. We just started circuits. Yep, nice, cool, perfectly on timing then for you. If you just started it, awesome. Okay, so intro to circular functions. So very basic stuff. Degrees, radians. These are a measurement of angles in your unit circle or otherwise. Everyone would definitely be familiar with degrees. You may or may not be familiar with radians at this point. We'll get into that in a moment. First, what is this unit circle? It is pretty much as you might infer. It is a circle, and given that it's a unit circle, it has a radius of 1 by definition. And it is centered at some origin, at least as far as the easiest way to picture the unit circle is to imagine it centered on some xy axis. So at the center of that is the origin, and any straight line drawn from that origin to the circumference of the unit circle is going to have a length of 1. It has a radius of 1. Now, because we know the circumference of any circle is given by 2 pi r, because the radius is 1, the circumference of the unit circle must therefore be 2 pi. What we do with this idea of radians is we start thinking about the angles within a circle, not necessarily with respect to degrees, but with respect to how much of the circumference is being covered in radians, in pi. Which is why we say that a full revolution is completed in 2 pi. 2 pi was a circumference, so if you have an angle of 2 pi, it means you've completed the full unit circle. If you were to go to halfway around that, you would just halve that number, getting pi. All we're doing is essentially moving away from working with degrees to now working with radians. You'll see the vast majority of what we do will have radians involved. Like if we go just to like 6b here, you can see all of that has got radians in it. Even these numbers that don't necessarily have pi, unless they specifically have the degree symbol, you assume it's in radians. We do have the degree stuff in there, but I can tell you for certain the vast majority of stuff you'll do is radians. So if you're going to pick one of them to memorize, definitely focus on that first. The conversion formula between them is fairly simple. It starts with the assumption that if there's 360 degrees in a circle and 2 pi is also considered a full revolution of the circle, then those two things must be the same. So we already have this equivalence between 2 pi and 360. Literally all you're doing is rearranging this equation for the thing that you want. So if you want to go radians, you would rearrange, and you're essentially left with radians is just going to be pi over 180 times your number, whereas to get it in degrees, you would multiply by the opposite, 180 over pi. We're just rearranging this, all right? Dividing both sides by 2 gets you the 180, and well, the pi can't really be simplified any further. So if you ever forget which way it goes, one way of remembering is to either just like start with this assumption here and rearrange what you want, or the other way I like to think about it is radians pretty much exclusively will always have pi in it. Now, we did see one circumstance where it doesn't, but that's because they're just being a bit weird. The vast majority of the time, it's got some pi in there. And so whenever I'm thinking I want to convert 2 radians, multiplying by pi puts pi into that equation. And dividing by 180, well, it's the only other number in there, so you have to divide by 180 once you know where you're putting the pi. The reverse is true, right? If I want to go to degrees, I want to take pi out of my equation, so I divide by pi. There's no mathematical background to that. That's literally just a memorization thing that I just picked up somewhere. Yeah, all we're doing is a multiplication here, effectively. I don't think we need to go into too much detail there. It's just if you want to go one way or the other, use the different multiplication to get there. You'll know you got it right if you don't have pi in your thing and you want to get degrees, or you do have pi in your thing and you want to get it to radians. Any questions about that so far? Are you covering circ functions for 3-4 from scratch? Yes. Yeah, I'll go through it from scratch. And some of the stuff that you would have learned like year 10 as well, like this trig stuff is technically like even pre-methods. I'll go through that at a bit faster pace, but if you want me to explore that in a bit more detail, just let me know as well. That's totally fine. More than happy to, because you need these fundamentals to fully understand what's going to work out well in the rest of the circular function stuff. Okay, cool. So the basic trig ratios, sine, cos, and tan, you guys should all be familiar with these, at least by name. They are all ratios of a right-angled triangle, and the adjacent, hypotenuse, and opposite are pretty much all written with respect to where the angle is located. So the hypotenuse is the only exception there. The hypotenuse is always just going to be the longest side length of your triangle. The opposite and adjacent can differ depending on where theta is located. So if your theta, the angle, is drawn here, whatever's not touching that angle, so this side and this side is touching, this side is not, that is the opposite. It is opposite the sides that it's touching. The side that it is touching, one of them will always be the hypotenuse, the other is the adjacent. So that's your way of remembering which way is which. As far as how you relate that back to your sine, cos, and tan, they are just the ratios of those different side lengths, one divided by the other. And the memorization that I'm sure all of you have come across would be the SOHCAHTOA memorization. Essentially, you've got it separated into your 3 separate little acronyms. The first letter of each stands for the trig ratio that's being discussed. So S for sine, C for cos, T for tan. And then the other 2 is the order in which you do the division. So OH means opposite over hypotenuse, and sure enough, there it is. AH means adjacent over hypotenuse. OA, opposite over adjacent. This won't be on a formula sheet, so this is something you'll have to memorize, but at least you'll have... when do you learn this first? Maybe like year 9? Actually, I think it might be as early as year 8. I think I've had a year 8 student that was doing this. So it shouldn't take you that much longer to get back on track. Yeah, as for how we then apply those to our triangles, it's going to be based on what information we have. All right, so in this case, we have the hypotenuse and the opposite, because it's opposite where the angle is, and you want to find sine. Well, sine is opposite over hypotenuse, so that over that. You can repurpose this for finding unknowns in a triangle as well. So in this case, we have the hypotenuse and we have the adjacent, as well as an angle. Now, we technically don't have the adjacent, it's an x, but our goal is to figure it out. So fundamentally, you just want to label what things you have. You have theta, an angle, you have a hypotenuse, and you want the adjacent. So your goal is to figure out which of sine, cos, or tan have all of those things in it. Which of them have an angle? All of them do. Which of them have a hypotenuse? That's going to be cos and sine. Which of them have an adjacent? Only cos. So you just plug in everything you need and then rearrange for the thing that you're trying to solve, wherever the x ends up, which in this case was the adjacent. In TeX-free, you just leave it exactly like that. In TeX-active, you may or may not have to evaluate that further. Just make sure if you are going between degrees and radians, make sure your CAS is actually in degrees and radians, or degrees or radians respectively. For you guys, because you do have newer models of the TI, you can literally just click that button there. That is a button. It's not just a heading there. My CAS does not do that. Alternatively, if you're Casio, you've always been able to click this. So you just click between that until it says deg or rad, depending on if you want degrees or radians. This is the... actually, no, this is worth discussing a little bit. So this might look more or less the same here. When you're solving for angles, things look a little bit different. So yes, we still have the opposite and the hypotenuse, so sine is the only thing that has the equation with both of those combined. But when you're trying to actually solve for the angle itself, what you're actually doing is doing the inverse circular function for that thing. So we know sine is equal to opposite over hypotenuse. Using the numbers, we get sine theta is equal to a half. The way the sine inverse works is kind of like... Actually, I don't think we have discussed this yet. Where would we? Oh, we would have discussed it briefly with like logarithms, where how you can wrap both sides of an equation with a logarithm. You can do the exact same thing with the inverse function of, well, not just circular functions, but actually anything else as well. So if we bring it to the handwritten notes, I'll sort of show you what the actual arithmetic of this ends up looking like if you want it to be very verbose with how you do things. This is going into more detail than necessary though, but it's nice to see. Just a quick question. So basically sine of the angle gives you something, but that's not the actual angle value. So yeah, that's right. So sine of the angle, whatever the angle is equal to a half. That is its value. If you want the angle itself, that's trapped in the brackets of the sine. Yeah. So as we'll see, what you essentially start with is your basic trig equation, which in this case is going to be sine theta is equal to a half. And what you're doing is you're wrapping both sides of that equation with the inverse version of the trig ratio that you had. So this will be, it'll look a little bit weird, and you may or may not have seen math like this before. Sine inverse of sine theta is equal to sine inverse, well, it's a bit bumpy here, let me move that down a bit so my writing isn't as bad, equal to sine inverse of a half. It's the same idea with logarithms, right? Like if you had x and 2 over there, you could do natural log x equals natural log 2. It's the same idea, wrapping both sides of an equation with a thing. Now, how we get to just saying theta is equal to sine inverse of a half is something you'll learn, I don't think we've done it yet, with composite functions. So there's this specific property of composite functions. You may or may not have done this yet, but any composition of an inverse function with the original function, so this is f of f inverse, other way around, f inverse of f of x, it always ends up equaling x, whatever's in the brackets there. Same if you did it the other way around, by the way. F of f inverse x. This is like all the way back in chapter 1 type stuff when you're doing your composite functions. So this is for any pairing f inverse and f. This is sine inverse and sine. And so when you see that theta is the thing in the bracket, theta is the thing that gets left on its own. Discussing why this is a thing is kind of beyond the scope of this lesson. We'll get to it when we get to it if we haven't already. I actually can't remember if we've looked at this before. But yeah, before knowing the unit circle, you would kind of just leave your answer as this. After knowing the unit circle, we will eventually know what this value is, but we'll get there in a moment. All that to say, essentially all you're doing, if you want to think about it the easiest way possible, is you're just taking the theta, bringing it out on its own, and then whatever this thing is, you're wrapping inside of a sine inverse. That's the gist of it, really. Cool, okay, that's it for the first section of that. Awesome. Now we can discuss how we can go a bit further beyond with the unit circle. So the reason why we had to discuss a bit about the basic trig ratios there is because I believe a good fundamental of the trig ratio stuff helps immensely with memorizing your unit circle and making it as printed in your mind as possible. Because, if I just sort of scroll back down, you'll have to have this thing in your head. That whole thing. It looks like there's a lot there, and there is. This does not go on your formula sheet, but we are building up to being able to have this memorized with very minimal effort actually required. Now, you will eventually do it enough to where you will just kind of know where everything is because you've seen it enough times, but the technique that we'll end up looking at will essentially mean you'll only ever be looking at this top right corner and using some inherent symmetries in the unit circle to sort of flip things around. So although you'll be able to, you'll need to know how to get everywhere on this circle, really all you need is this bit here memorized enough, and then use some symmetry stuff to flip things around. And understanding how that all works comes with a nice fundamental of your basic trig ratios, because what we start looking at are coordinates that exist on the circumference of the unit circle. Essentially, you could draw some straight line connecting the origin to any point along the circumference of the unit circle, and what you'll find is the coordinate of that is given by cosine theta, sine theta, where cosine is the x and sine is the y. The reason that is because if you imagine your radius drawing there as a hypotenuse, you can essentially complete a triangle, right? It's going to have some horizontal component and some vertical component. Anyone doing physics here, this is basically what you do when you're doing your projectile motion stuff. You split things up into the vertical and horizontal components. Anyone doing physics will be very familiar with sine being the vertical component and cos being the horizontal component. But why is this the case? It's a simplification of the sine and cos ratios, opposite over hypotenuse, adjacent over hypotenuse. The reason we're able to simplify things is because the hypotenuse is equal to 1 for any given unit circle. So essentially, this denominator always just flips out, just disappears. It goes to 1, and so what's left is sine is always the opposite of your angle. So the angle's there, opposite would be this bit. And since that's the vertical bit, that's going to give you your y value. Adjacent, exact same thing for cos, right? Adjacent is the part that is connected to the angle. The angle's always with respect to the origin, by the way, which is why, again, horizontal component, cosine. So having good fundamentals there, if you ever get confused as to whether it's cos or sine first, which one's the x or the y, just start by drawing this little picture and be like, okay, I got my triangle, my hypotenuse is 1, what must these therefore be? Okay, that's cos, that's sine, got it. Essentially relating things back to stuff that you'd be ideally more familiar with, given you've seen it more times in schooling, and compounding on that to help you with these other things. Any questions about the fundamentals there so far? There's a whole spiel on why tan theta is equal to gradient here. You don't really need to know all of this. You just sort of need to know that the gradient can be given by tan theta. The reason why, just briefly, is because if cos is the x and sine is the y, and any line that you draw from the origin to the unit circle itself is a straight line, you're essentially doing rise over run. So to find the gradient of any given line, you would do sine divided by cos in this case, because it's y divided by x, since your origin 0, 0 is the other point. But one thing we know is tan is sine divided by cos. So if gradient is sine divided by cos, and tan is sine divided by cos, then gradient is tan. This is something you'll use more so when you're doing calculus, where you'll have to be finding gradients in new and interesting ways and combine them together to create new equations. Kind of like how in other areas of study you'd have to have like, oh, here's one way of calculating it, here's another way. Ah, they're the same thing. And then you can solve for an unknown. But not super relevant for what we're doing now, just a nice little insight for later. Okay, let's start getting some of the unit circle exact values done, and probably at this point we'll start looking at doing some practice questions on them. So, easiest way to start breaking this down is to start looking at the quadrant boundaries. So just like how the XY axis has quadrants, where quadrant 1, 2, 3, 4 are located in those spots, the same is true for the unit circle. I've just seen a question come through. Are we going to look at graphs today? No. Graphs will be later on. This is all about going to do the actual evaluating or the solving of the circular functions. Graphing we may do next week, if not the week after, because I'm fairly certain a lot of this won't be covered. If you're keen on doing graphing stuff, let me know and I will change things around for next week. Alternatively, there's also the pre-recorded lessons and last year's version of these, if you want to have a look at those as well. But no, for today we'll just be doing the solving and evaluating. But okay, so we've got these quadrants, and because we're working with radians, we're going to essentially mark all of these quadrant boundaries with their radians equivalent. So 2 pi is a full revolution, pi is therefore a half revolution, half of that again is therefore going to be a quarter revolution, and then you can kind of just backfill in with what this one would have to be, right? These are all separated by pi over 2, which is why we now have 3 pi over 2 on the bottom. You will be required to know the sine, cos, and tan of all of those. Or in other words, the y, the x, and the gradient of those things. Which is why it shouldn't come as too much of a surprise where all of our values are now going to be either zeros or ones, or the negatives of those. Because if the radius is 1, then anytime you're on the absolute boundary, or the quote-unquote corner of a circle, if such could be considered, you've got an exact vertical or horizontal line. And so for that reason, you know, if you think about just this one, for instance, you're going right, as far right as you possibly can with no vertical component. The entire radius of 1 is going horizontal. So your x, or in other words your cos, is going to be 1. And your y, your sine, is going to be 0. 0 for sine, 1 for cos. And if you think about the gradient of such a line, it's perfectly flat. Gradient 0, tan is 0. So even though we don't necessarily have to think about tan as a gradient right now, I think it's kind of nice to make it easier to know these values, because rather than have them memorized, you can just think, oh, it's a horizontal line. Gradient 0, tan is 0. Awesome. Similar for y, we have some undefineds in here, right? Like perfectly vertical, pi over 2 and 3 pi over 2. A fully vertical line has an undefined gradient there because you're dividing by 0. You have no run. And so for that reason, the gradient's undefined. Tan is also undefined. And so yeah, just thinking about things in terms of where they would be positioned on an XY axis tends to be the easiest way to think about these things. Any questions about how that works? I think there's going to be a chapter section on them. I don't think it goes any further. Cool. Okay. How to go from here? I'm trying to imagine, do I need to go any further? Oh, I don't have my other note up. Whoops. Let me go find that real quick. Evaluating. There we go. We may need to have a look at this. But for now, what I'll do is I'll just grab a screen grab of this and we'll see how we go. Because I can see there are some that are going to be more complicated than just this. But we'll get there when we get there. Alright, I'm going to do a screenshot of that specifically in the chat, and we'll see how we can go from there. Do we have any that are doable? Not really. Okay, I'm just going to make up my own then. Well, that means I can just leave this up. So we're just going to basically test some interpretation here. These should be fairly easy questions. You literally just have to look at the table and tell me what number goes to what. We won't spend too long on it, as long as people are still getting it right. So I'm just going to make some up, and we'll see how we go. Sine of 3 pi on 2. Based on the table and the picture that we have there, what is sine of 3 pi over 2 going to be equal to?
-1.
-1 is correct. How do you know that?
Check the table.
Check the table? Cool. Yeah, you saw sine, you saw 3 pi over 2, and the value, -1. Nice. I don't know, we'll do like maybe 2 more. Let's go cos of 2 pi. Cos of 2 pi.
0.
Cos of 2 pi. So how do you know 0?
Because isn't it a full rotation of the circle?
It
so
is.
Then
So yeah, so full revolution of the circle would get you here, or in this sort of section in the table. Is cos the x or the y though?
Oh, yes. It would, yeah, okay.
Yep.
Yeah.
So you're halfway there. You understood that 2 pi got us a full revolution. But yeah, knowing that cos is the x specifically gets you the 1 instead of 0. No matter. Oh, sorry, 1. There we go. And I don't know, let's do a tan this time. We'll do a tan of pi over 2. Who wants to take that one? And it's a bit of a weird one because it doesn't actually go on the unit circle. You kind of have to use either your own method or use a table.
Is it infinity? Does it go straight up?
It goes straight up. I didn't hear the first bit that you said though.
It's infinite or undefined?
Yeah, undefined is technically more accurate there, because this would be a little fun discussion. So the reason why it's not necessarily infinite is because of the hyperbola graph itself. So if you guys had done the hyperbola graph, it is 1 over x, and what we end up finding is it kind of looks like this. Now, one interpretation of it, when you divide by 0, you should get infinity. That would be as if coming from this right-hand side, where your x values are getting closer to 0 from the positive side. We can see this shoots up to infinity. But equally true, if we imagine coming from the left-hand side, we also have this opposite effect going down to negative infinity as well. And so, infinity or negative infinity, we're unsure. We don't know which way to go, which is why we say undefined specifically. That's a nice little revision of that. But yeah, that's pretty much it. Use a table if you prefer, or use the methods of the sine, cos, and tan being gradients and x, y coordinates, depending on how you want to do that. If we look at the book stuff itself, we'll notice that we have much bigger angles. So not just a single revolution of the unit circle. We start needing to figure out how do we do more than just a single revolution. So for that, damn, I did this when we did interquadrant angles afterwards. You'll see some bigger angles or different types of angles than you'll expect. Work with me on it for now though. So have a look back at the screen share. Basically we're going to have a look at what happens if we can't locate the angle that we're looking for directly on the unit circle. So this example here, cos of 7 pi over 3, we're going to skip a little bit and look at the full unit circle. There's going to be a bunch of different pi over 3 type angles in there, and what we'll notice is that we cap out at 5 pi over 3, or technically 6 pi over 3, which will simplify down to 2 pi. All that to say, this does not appear labeled exactly on the unit circle. So what do? There's a couple of ways you can handle this. If it's small enough, you can literally just count sections around the unit circle itself. So for instance, here's all the pi over 3 type angles. You've got pi over 3, 2 pi over 3, 3 pi over 3, which simplifies down to pi, so on and so forth, and you just keep counting around until you hit the thing that you want. They will end up overlapping themselves. So essentially 7 pi over 3 is in fact the same thing as pi over 3, and for that reason we just use that spot on the unit circle, whatever that one was. In the context of something like sine of 3 pi, for instance, you would look at your unit circle, or we can use our simplified version. Sine of 3 pi, we can see there's no 3 pi on there. But we know pi is here, 2 pi is here. It should mean that 3 pi is now going to be here. Because you imagine counting around, if pi is always a half revolution rather, then every copy of pi you're going counterclockwise around the unit circle until you hit the spot you're looking for. I see you got a question, Taihan.
Yeah, wouldn't it just be easier to think of it as multiples? Like, for example, the 7 pi over 3, the only pi over 3, I guess, point on the unit circle is pi over 3. So you know that that's the only multiple, so it's got to go back there anyways.
Only multiple of it. Okay, so how does that differ if I said, like, instead of 7 pi over 3, I said 9 pi over 3? How do you adapt your idea? Because there are these as well.
Yeah, but since it's 9 and the only, I guess, numbers you could divide it was like 1 or 3, you'd know it'd come back to the 1 pi over 3.
Well, 9
Is
pi
that
over 3
correct,
won't
or-
be 9 pi over 3 won't be here.
Oh, okay.
9 pi over 3 actually fully simplifies. You've got 3 pi from that. So it's not necessarily that it's a multiple of this and so it should go back there,
Yeah.
because the same logic would apply to like 2 pi over 3 over here. Basically that method of counting around, and that's only one method, by the way. You do have an idea, which I'll put a nuance on it so that does work. But the idea of the counting method there is they're sections of the unit circle itself. And so if you know that pi over 3 just means 3 sections of half a circle, that means 6 sections are a full circle, and then you just count around from there. But that really only works for smaller things, right? If you have a big thing like 55 pi over 6, that's not going to work. So what you've alluded to is there are some symmetries that you can use, just not necessarily that one. If you do have quite a big angle that you're working with, what you can do to make life a lot easier is to split it up between an integer value of pi and the fractional value of pi. So in other words, you're basically just creating a mixed fraction. How many times does 6 fit into 55, and what's the remainder? It fits 9 times with 1 remainder. So you get 9 pi plus pi over 6. You're taking this nasty thing into something a lot easier to work with. Why is it easier to work with? It'll go back to what I was just discussing with the 3 pi example, right? Which was we had 0 pi over here, 1 pi over here, 2 pi, 3 pi, 4 pi, and so on and so forth. What we notice is that all the odds end up on the left and all the evens end up on the right, just based on how that works, right? If you're counting in pi starting from here, then the first pi will always be on the left and the second will always be on the right. All the odds on the left, all the evens on the right. So the fact that we have 9 pi in there as a quotient, if you want to think of it that way, means that when all is said and done, you can basically now just start here, because you're going to do it 9 pi times regardless. So because you know 9 is odd, you can now just start there. Then whatever's left over, in this case it's pi over 6, you now just count to the next thing that has a denominator of 6. In a context of over here, right, it could be that we had 49 pi over 2. You would split that up into the whole version and what's left over. What's that going to be? So 24 pi, and then pi over 2 left over. 24 pi is even, so we would start there. Pi over 2 remainder, we end up there. So knowing the little trick between the evens and odds there will tell you where to start, and then you're left with a very easy angle to count around afterwards. And yeah, whether it's sine or cos will then depend on whether you give the x or the y at that spot. Fair enough on, well, should I clarify any of those approaches? Either the counting method or the, I guess you can call this the division method, whatever you want to call it. Cool. Oh, hang on. Can we do some practice on bigger numbers? Absolutely. Right here. So let's give it a shot. I mean, there was the 49 pi over 2. I kind of said that one out loud, but didn't actually show any working for it. So let's give that one a shot. Okay. cos of 49 pi over 2. So with the bigger numbers, our goal is to basically figure out how many times does 2 fit into 49 as a whole number, and then whatever's left over. So let's try and just do it. How do we split 49 over 2 into a mixed fraction?
24 pi and then 1 pi over 2.
Yep. Nice. That's step 1. Split it up into the mixed fraction. Now what do we do with that split up?
Because 24 pi is even, so you know it's going to be on the right side of the unit circle. So you start from there, and then pi over 2 is going to go 1/4 of the way.
Yes, it is. Awesome. Do you know what's located there, the coordinate?
0, 1.
0, 1 is correct. Yeah. Now, which of those match up to cos?
This is the 0.
The 0, yeah. How did you come to that conclusion?
Because the cos is the x coordinate and sine is the y coordinate.
Awesome. Yeah, it's good that you're there. For those who aren't able to get it off rip like that, it's fine. You can just refer to the table and the actual picture. Just do that enough times to where you eventually where you can start doing this off rip like that. Yeah, we'll do one more type of archetype there. So let's do sine. I'm making this one up of 301 pi. Big number, but it's actually probably the easier one to do.
You can just take 300 pi first, then because that's even, you'll start from the right.
Sure.
And then you need to add the additional pi, so you can just go half of the way.
Yeah, that's cool. Yeah, you can do it that way if you want to default to finding it even first and then going afterwards. The other alternative is just, it's odd, so odd is left. But yeah, perfectly fine. Nice. So yeah, anytime you have your perfect integer values of pi, those tend to be the easiest ones to actually work with, no matter how big they are. It's more so the divide by 2 or other denominators that start getting a bit weirder, because you've got to actually think about what the split is. If you look at stuff like question 3, you'll see definitely more denominators, but we've only discussed the pi over 2 types and the whole number types so far. You'll also see some negatives in question 1, which we'll discuss now, I think. So let's go back to the screen share. How do we work with negatives? So definitionally speaking, negatives just mean you're going in the opposite direction of the unit circle. So one way of thinking about it, not necessarily my preferred way, is to, instead of labeling all of your things in the anti-clockwise direction, you label them in the clockwise direction. So now pi over 2 is down here as opposed to up there. Now you just put negatives on everything. That's what's actually happening. However, I think a much better way or easier way of working with negative angles is to follow what I think is a simple 2-step procedure. Basically, step 1, pretend it doesn't have a negative on it, and just solve it the exact same way you would do if there was no negative. So 7 pi over 6 is one that just exists on the unit circle. If it was anything else, we would be using the tactics we discussed earlier. We found 7 pi over 6. Nice. Step 2, literally just flip it vertically. So wherever the corresponding spot is on the unit circle for that thing is the equivalent negative version of that angle. Because if you think about what this is, it's a negative applied to the x spot of your circular function, sine x. That's a flip. And so essentially what you're having is this vertical flip of things. Now it's a little bit different. I think the analogy doesn't really work because technically you'd imagine the negative to be out here instead. So that's kind of my fault, but basically imagine it as a reflection, right? You're flipping upwards. For those who aren't too familiar with the unit circle, you're basically just matching the denominator to its equivalent on the other side. So you'll see they've got 3s, 4s, and 6s, 3s, 4s, and 6s, 3, 4s, and 6s everywhere. So when you're doing this flip, you're flipping it vertically. And yeah, the 5 pi over 6 spot, if we have a look at the negative component, is negative 7 pi over 6. So in 2 steps, step 1, pretend it doesn't have a negative sign and just find that on the unit circle with whatever method you need to. Then flip vertically to account for the negative and give that as your coordinate that's required. That's the idea. Let's test it. So we have this negative 5 pi over 2 going on. Step 1, what do we do to simplify things?
You can simplify it down to 2 pi and then adding pi over 2.
Yep. There was an unspoken step in there, which was pretend it doesn't have a negative to begin with, and then just work it as positive. So yeah, that's it. What do we do with that information?
And then, yeah, because we're still pretending like the negative's not there. So because it's 2 pi, you just start at the regular starting point on the right.
Yep.
And then go anti-clockwise by pi over 2, which means we'll go a quarter of the way up to the top.
Yep.
And then we factor in for the negative, which means that we reflect across the x-axis, which means we end up at the bottom.
That's it. Perfect. Do you remember the coordinate here?
The coordinate would be 0, -1.
That's it. And which one of those goes for cos?
Cos is x and sine is y. So that means we're solving for cos, so cos is 0.
Cos is 0. That's it. Yeah, that's pretty much it. It's just one addition to the stuff we just discussed earlier. If you have negatives in there, pretend there's no negative, and then factor in the negative afterwards. Cool. Okay. That's all. Actually, that's all we need for the evaluating stuff. So the methods we've just discussed there is everything you need for when you have an angle, but you're trying to find the value. Now there are more angles and more values to look at, but as far as what you're doing with those, same procedures. You're either finding it directly on the unit circle itself because it's easier, or you might have to employ one of those techniques to find where it is and then go from there. We've looked at this a little bit already, but the interquadrant angles. So we've kind of already done a bit of a sneak peek of the pi over 6, the pi over 4, and the pi over 3 type angles. They also come with their exact values as well. This one you kind of just got to memorize. The bare minimum you have to do is know the pi over 6, pi over 4, and pi over 3 type angles, and the values half, √2/2, and √3/2. So it's not too bad. Everything has the same denominator of 2, and you're essentially just counting up 1, 2, and 3. That's how I would think about it. As for knowing which one goes to what, we'll discuss that next. Also, as for tan, how do you then go there? Once you know your sine and your cos, you can actually just calculate your tan, because tan is sine divided by cos. So if you're like, look, I don't want to memorize shit, I just want to do the absolute bare minimum, then these are technically calculatable. And that's what I actually did in the actual exam. Wouldn't recommend it, but it is what I did. I calculated them instead of memorizing them. Cool, okay, so how do we know which goes to what? This is where you get to sort of double dip with thinking about things in terms of where it would exist on an XY axis. So first things, the angles. Those should be fairly obvious, where you're essentially doing things in ascending order, like we saw earlier. Pi over 6 is the shallowest, followed by pi over 4, followed by pi over 3, and well, we already know the 0 and the pi over 2 from earlier. You're just writing those in ascending order. Now, as for where the half, √2/2, and √3/2 belong, that'll depend on the relevant or relative XY locations of what you have. So if you think about the pi over 6 angle, being that it's the shallowest angle, it means that horizontally speaking, it's the furthest along. So if you see where all of these points intersect the x-axis, if you were to draw a line straight down, it's the furthest along the x-axis. So for that reason, cos should get the biggest number because it's the furthest along the x as compared to all the others, √3/2. Inversely, it's also going to be the shallowest as far as height is concerned. If you look about, because it's the shallowest angle, all the other ones have a higher height on them. And so for that reason, since this is the lowest height, it gets the lowest of the values for y. Pi/4 is midway through. And, once you have one of them, you can fill in the rest, right? If this is the furthest along, then this will be the next furthest, and this will be the shallowest. And so you're essentially ordering them in ascending or descending order, depending on their heights or widths. That's probably the easiest way to think about it in terms of how far along the axis it is. That's quadrant 1 there. Any questions so far? Okay. Tan is not on this. There's a couple of ways you can do tan. I already mentioned the first one, which is just calculating it. So tan is always sine divided by cos, or the y divided by the x. And so you can just do that for all of them. Or if you want to memorize 3 more values, which is probably what I recommend, because it's not that much more, you now have √3, 1, and √3 on 3. That could also be rewritten as 1/√3 through the surd, rationalizing the denominator. Point being, you're still doing an ascending order of things with the numbers. Now, the way in which you're doing the ascending or descending order is dependent on the steepness of the angle, because remember, we're talking about gradient with tan now. So because pi/6 is the shallowest or least steep gradient, it gets the least biggest number, or smallest number. And then, as the lines get steeper and steeper, so too do the gradients, so therefore the tan values should also increase as well. I'll just see a question here. If you know the degree and radians for the first quadrant, you can just multiply it through. Yes, but I just want to see your example real quick. So 30 degrees goes to pi/6, 240 goes to 8 pi/6, which is equal to 4 pi/3. Yeah, basically. So we're going to discuss that, which is how do you get to the other spots on the unit circle. And it seems like you've interpreted it just well. Yeah, you can do symmetry stuff like that to get there. But before I discuss that any further, fair enough on the tan related stuff. Okay. Cool. So that was tan, sine, and cos. Yeah, okay. So how do we get to the other spots on the unit circle? As I said before, every single quadrant of the circle has a pi/3 type angle, a pi/4 type angle, and a pi/6 type angle. All of them are there. And so what you might start to notice is the numbers that are mirrored across the unit circle in those relevant positions. Whoops, I drew that a bit wrong. Let's do that and that. I'm highlighting the pi/6 or as much as I can for the pi/6 stuff. And what you notice is the things in the brackets, the actual coordinates themselves, are basically the same, with the exception of a few negative signs. Before I give it away, does anyone know or can spot a pattern as to why there would be negatives in different spots, but otherwise the same?
Because all the coordinates are the same distance from the origin.
Yeah, that's one absolutely nice way of thinking about it. They're all the same distance from the origin. How do you account for the difference in negatives versus positives?
What do you mean?
Yeah, so like this one's fully positive, √3/2 and positive 1/2. This one's got a negative on it though. And this one's got a negative.
Oh, it's just like you can just think of it like basic quadrant coordinates.
Yeah, exactly. This is on the left side of the x-axis and above top of y. It's on the top, so y is positive. It's on the left, so x is negative. This is bottom left, so double negative, negative x, negative y, so on and so forth. Right. So once you know these quadrants fine, you can now flip them over perfectly, and all you have to do is know, hey, it's on the left, so x is negative. It's on the bottom, y is negative, so on and so forth. That gets you all the values split across everything nice and easy. As for how you label these themselves, that's pretty much just counting around the unit circle, at least for now. We can look at some further symmetries to do less counting, but in reality, it's not that hard to just sort of count around things. So for instance, if you just think about like the pi over 4 bits, well, 2 pi is a full revolution, pi is half, pi over 2, pi over 4. Okay. So in other words, basically whatever your denominator is how many times you're splitting half a circle. So pi over 4, you're splitting it into 4 parts. You got 0th, 1th, 2th, 3rd, and 4th spot. And yeah, you just duplicate that over. And simplify things. 2 pi over 4 is just pi over 2. 4 pi over 4, just pi. That's why, technically speaking, you don't even really need a pi over 3 memorized either, because pi over 6 is factored into pi over 3, right? Because pi over 6 means you're splitting this up into 6 spots. 2 pi over 6 does split down into pi over 3. That's getting a bit dicey though, trying to not memorize pi over 3, because it is paired with one of the fundamental values. Bit hard to get around that, but technically doable, should you really wish. And yeah, all we're doing is counting here, and that'll get the actual values themselves. Yeah, all this is the written version of what I was just discussing there, of how you can flip things over and count them around. The degrees angles are in there as well. You barely need them. A SAC might need it though, is the thing, which is why it's still worth having them there. And the book also does it a little bit. Where's the book gone? There we go. Yeah, it's shoehorned in right at the very end. And they're like, yep, that's where degrees is going. These are not degrees because there's no degree symbol in any of them. It's still radians. So less important. If you're doing this for the first time, focus on the radian stuff specifically. That's pretty much it. So we got up to what is effectively, we know the angle, or we're told the angle, and we want to find the value that corresponds to it on the unit circle. What we'll then start moving on to is, I don't know which way we want to do this. If we want to go for the solving, which is where we don't know the angle, we do know the value, or we could potentially move on to some of the symmetries, because in this chapter section, we do end up doing some of that stuff. So you see this pi minus data, pi plus data, that's the symmetries related stuff. Same with 6c over here. I think probably the best thing to do would be to move on to solving, because it's the next adjacent thing. We're not going to have much time to go through it in super detail though, but we'll go as far as we can. Before that though, are there any loose ends I should clarify from what we discussed so far? Actually, the Friday review class will be a good way to finish off the rest of this. So even though we only got through half the content here, we could probably go through the rest of it in the review class. Anyway, solving. Solving is a bit of a different procedure, but isn't going to differ too much. Oh, got a question here. How does Q4 and 5 work for 6b? Yeah, that's what I was discussing there. This is a completely other document. It's in the document 9, where we start looking at all these sort of symmetry things and going into more detail as to how you can flip things around. It's all of this stuff, which a lot of formulas there, but there's, again, nice and easier ways to think about things. We'll cover that in another lesson though. Or if you want, there's the videos I've already done, or last year's group classes, if you want to suss those out as well. Let me know. But for now, solving. So, as I said before, it's where you don't know what the angle is, but you are given the exact value that it corresponds to. One of the challenges here is that you may have already noticed that there might be double ups of values. Like for instance, cos being root 2 over 2 belongs to pi over 4 and 7 pi over 4. Right? Both of those have the x coordinate being root 2 over 2. Not actually a problem, because what you're given is a domain for which you are allowed to give all the possible values for that solution. So a domain of 0 to 2 pi simply means you have one full revolution of the unit circle to work with. And so you give both of those examples. Essentially, you start by looking at the value, it's root 2 over 2, and the circular function, it's cos. So in other words, we're looking for all of the x coordinates that are equal to root 2 over 2, which is what I was highlighting there. Then all you do is you look at the angles that those correspond to, or you have it pictured in your mind, however far along the journey you are, and you just give all the angles that are associated with it. That's it. X equals that, comma, x equals that. Or if you wanted to, you could be a bit more verbose and say x is an element of curly brackets, those two with comma separated. Sometimes you might have to rearrange your equation to get there. So this one doesn't really look like it's where you want it to be. You pretty much always want to get it to a spot where you have circular function exactly on one side and the exact value on the other. So this is basic sine equals one of our exact values. And again, same idea. It's sine, so we're looking for y values that are equal to root 3 over 2. Where are all the y's equal to root 3 over 2? There and there. And you know, it's positive, so you can now start thinking about, instead of looking at literally every single value, because you know it's positive y, you really only have to look at this top bit. And because it's the biggest of the exact values, you know that belongs to the pi over 3s. These are sort of little techniques you can do to speed things up. But yeah, exact same procedure, you give the angles at the end. Any questions as to how that's worked? Let's see, should I go any further? We'll do one example of that just to make sure we've got it in. So I'll pull up the unit circle for reference, and I'll just make one up that we'll try to solve. We'll do it for 0 to 2 pi again, so one full revolution, keep it simple. Let's do sine of, where do I want to go? Let's try 5 pi over 3. Oh, what am I saying? Okay, let's change that again. We'll do sine of x, because that's the question we're trying to do. And let's say -12. We'll do that from 0 to 2 pi. What are all the x, so angles, that give us sine equals -12? Got the unit circle on a screen share if you want to refer to that as well.
Sine equals -1/2, right?
Yeah, sine equals -1/2, that's right.
So that means the values could be 2 pi over 3 or 4 pi over 3.
2 pi over 3, 4 pi over 3. Double check what sine is supposed to relate to.
Oh, okay. Yeah, I got it. It's going to be pi over 3 or 5 pi over 3. Oh, sorry. I messed it up again. It's going to be 11 pi over 6 or 7 pi over 6.
Yeah, there we go. So
Sorry, I just messed up the signs.
No, you're fine. So what was the conclusion there? What did you have to look for in the end?
Well, because you know that sine's relating to the y coordinate, so you just find where the y coordinate equals -1/2.
That's it. So -1/2 there, and that was 11 pi over 6. -1/2 there, and that's a 7 pi over 6. Yeah.
Are there any questions where you'd be expected to give a negative answer?
Yeah. So that was the bit that I was debating whether or not I should work with, which is if you have a look back at the screen share, you may or may not have 0 to 2 pi. You might have -pi to pi. So because you've asked, we'll have a look at it. the way you handle possibilities with negative angle solutions is you split it up into two parts. In one section, we're going to do all positive solutions, which is exactly as we just discussed. You just go around the unit circle as far as you can. So in this case, the full positive bit would be from 0 to pi. So full positive would be just looking at this top hemisphere of it. And you would give all the possible solutions for sine equals 0 in this case. So sine is y, and the y coordinate being 0, that's going to be there and there, which corresponds to the 0 and the pi. That's in the positive direction. So we start with those solutions. Next, we then go in the negative direction, which means counting around backwards, right? 0 to negative pi now. So in other words, we're now looking at this bottom quadrant, but we're treating everything as if they are negative angles instead. Whatever
So
method.
then the question we just did, what does the negative before the half
Oh, yeah.
impact?
So because that's in the exact value spot, it belongs on the coordinate. So the only time you ever give negative angles is when domain goes into negative spots, because x being domain, x is in the angle spot, right? And so because domain goes negative, angles can go negative. What happened before when we had okay, these are both positive. What happened before when we had the half being negative itself was, because it's in the exact value spot, it's on the right hand side, we're looking for where the coordinates end up being the negative. So that's the difference there. Is it fair enough, the difference? Sweet. But yeah, so because we had negative domain, we can possibly have negative angles. And that was a matter of counting backwards, which if we're looking at this negative hemisphere of it, that spot counts again, but it's now negative pi since you're counting in a counterclockwise way, which is why we also have our negative pi in there as a solution. Yeah, okay. That's time. If there's anything further to clarify, please let me know. I'll stick around for a bit. Even if you want to go and finish this one off, because that's actually a lot. That'll be best saved for later. But yeah, anything further to clarify, happy to do so in the next couple of minutes. Otherwise, I'll leave you to enjoy the rest of your day. I'm debating whether or not the Friday should be covering new content, because we do technically still have the rest of this, that. But it may or may not be its own lesson. We'll see. Let me know if you have any thoughts on whether you want it to be a review or otherwise. I'll do that. Otherwise, I'll see you when I see you next.
Thanks.
Thank you.
Cheers.
Thanks.
No worries.